Welcome to our first e-learning session. We are in the midst of chapter 2. I remind you that we are discussing the postulates of quantum theory according to the way we presented in this class. We have already seen postulate number 1, that was about the states being described by a vector space with some rule. And we were in the discussion of postulate number 2 that relates to measurement. I will remind you something I said last week about the measurements because it will be useful for the thing that I have to say next. So the postulate was saying that, remember what a measurement is. In general, a measurement can be seen as something where I have a box, I come in with a quantum state, a system to be measured. This box gives away some information, and possibly the states, the system continues with updated information. Now, we discussed the fact that in this course we will focus on the most perfect measurements, the ideal measurements called projective measurements, in which this some information will be a pure state. Remember, a pure state is a state of maximal information, so which means a vector, and the updated information will be that state. So if the pure state is phi, then now the system is found in state phi. And we have discussed how the probabilities for this process to happen, for entering with state psi and finding the result phi, were given by the Born's rule. Probability of finding phi given psi is psi phi scalar product modulo square. Okay, so now what are we going to do is the following. This is something that, again, I'm sorry to repeat this sentence a few times, that some textbooks don't put it very clearly. So far, we have done everything that is technically needed to describe a measurement. So a measurement, a projective measurement, is equivalent really to a basis. I will do it for finite dimension. The infinite dimensional cases we will discuss a bit later in chapter 4, but it is very similar. Now, very often, although again I repeat, not always, a measurement is a measurement of a physical quantity. Like if you want to measure the energy, and you find that, for instance, that this state is a state of energy E1, this state is an energy A2, this state is a state of energy AED. Okay, so this would be like, so these are vectors that describe the properties of the system, but actually these vectors in particular represent, for instance, in this case, for this example, a situation where the energy has a given value, 1 electron volt, 2 electron volt, 7 electron volt. In this context, when you are measuring a physical quantity, also called observable, in this context, you may want to ask other questions, not just what state I found after one round, what is the probability of finding this state. And we want to ask, for instance, what is the average value of this physical quantity, of the energy? What are the standard deviation of the energy? So you want to compute things that are statistics not on the states themselves, but on the physical quantity. So we have to describe how to go about this. Okay, so now, to have an idea, I will start with how to describe the average, and then you will see a pattern coming out. So what would be the average value of this quantity E? In the lecture notes it's written A, so that either you get confused or you see that these letters don't matter. What would be the average value if I repeat this process many times? Well, you know how to define the average value, right? Is the sum over all possible outcomes of the value of the outcome times the probability of finding the outcome. Now, what is the probability? Let me change color just for fun. In state psi, what is the probability of finding the outcome k given phi? Well, this is given by the Born's rule, right? So this would be psi phi k squared. So let me open up this expression now. Sum over k, ek, and now we have here psi phi k psi, because remember that this is the complex conjugate of these, so therefore the product of these two complex numbers is exactly what we want. Now, again, this may be one of these expressions you're not very familiar with, but let's check the structure of this expression. So here we have a line vector that does not depend, sorry, it's a bit too small for you, right? Does not depend on k. Here we have a column vector that depends on k, a line vector that depends on k, and a column vector that does not depend on k. The whole thing multiplied by a number. So, you see, I could here have a matrix which would be the projector on phi k. And so if I continue this expression, now that you see how the structure is, I could bring this vector out of the sum, I could bring this vector out of the sum, and keep the sum in the middle. And what I would get is this. Psi, sum over k, ek, phi k, psi. And here you see appearing an operator that has the phi k as eigenvectors. Remember, it's a basis. And the ek as eigenvalues. Now, in the case of energy, these are real numbers. So therefore, this is a Hermitian operator. Right? It has orthogonal eigenvectors, so it's normal operator with real eigenvalues, so it's Hermitian. So let me write it here. What we have seen is that the observable will be represented by an operator. Now let me move back to the notation A. Now it's no longer energy. For the example, it's just any physical quantity that is a sum over k, the eigenvalues, and its eigenvectors. And if the eigenvalues are real, then this guy is Hermitian. This is what people call an observable. Now, I went through this clear explanation to try to convey the following message. Again, in some textbooks you will find something like every measurement is represented by a real value. But I don't believe so. You can come here to CQT, go to the labs, a measurement is a detector that clicks. You are not obliged to associate a real number to that thing. You can associate a color, you can say just this is detector A and detector B. You don't need to do that. Now, when you do physics, many quantities, position, momentum, energy, angular momentum, spin, and so on, these things have actual values. Therefore, it makes sense, and these values are usually real. Therefore, it does make sense to discuss the observables, okay, the Hermitian operators. I hope this gives you a little bit of critical spirit, right? So let me repeat it again. A measurement is defined by a basis. If it's a measurement of a physical quantity, you can just as well represent it by the Hermitian operator that represents that physical quantity that is diagonal in the same basis and has the eigenvalues, the values of the observable as eigenvalues. In this case, you find the rule that you find in most textbooks that we would say, what happens during a measurement? What I can find is one of the eigenvalues. Why? Because what you actually find is one of the eigenvectors, and to that eigenvector, you're associating that eigenvalue. Okay, now you can go and read your favorite textbook on this topic. Now, the next topic I have to do is something about what is called uncertainty relations. I will erase all these. Sorry for that. Of course, it takes a little bit of time to erase. So, we have seen that one of the elements of the postulate 2 was that, remember, in postulate 2, one of the points was that the intrinsical randomness, right? Intrinsic randomness of outcomes, individual outcomes. Now, when is a measurement not going to give randomness? Well, so not random, let's put it here, not random, it would mean that the probability is 1. 1 for, let's say, phi 1, and 0 for all the others. Okay? This would be, it's a bit better. This would be the case when a measurement is not random, when the result is certain. Now, if I write again my observable, when is the result not going to be random? Well, when I come with an eigenvector of, when my input state, psi, is one of the k's, k bar, right? In that case, I will get a k bar. If k bar is equal to 1, I am in this case, right? So the probability of finding a1 would be 1, and the probability of finding any of the other a's would be 0. And here comes the very important theorem that of the commutators. Suppose I have two physical quantities, position and momentum. Okay, position and momentum are not like this, and the spectrum is continuous, but just for fixing the ideas. So I have two physical quantities, A and B, that do not commute. Then there exists some eigenvectors of A that are not eigenvectors of B. Remember, this is the fundamental theorem, right? If A and B have a common set of eigenvectors, if and only if they commute. Okay. What does that mean? Well, it means that if I make a measurement, if I have a state, a source that produces a state, and I can make either a measurement of A or a measurement of B, very important, not first a measurement of A and then a measurement of B, but either a measurement of A or a measurement of B. This is the setting of the uncertainty relation. If I can do either A or B, let's assume, for the sake of the argument, sorry, that A is certain, B, the outcome of B, may be not certain. Usually, often not certain. where by often I mean something that, again, because of degeneracy, you can have some strange things. You can have situations where these two do not commute, but some of the eigenvectors are common. Okay? This theorem guarantees that not all the eigenvectors are common. Some may be common. And let's say that the state here is an eigenvector of A. So psi is equal to A1, but is not an eigenvector of B. Then B would not be certain. Okay? Again, this is the framework in which later we shall discuss the fact that you cannot measure position and momentum, not at the same time, but you cannot have a state such that position and momentum have both a certain outcome. If someone wants to know more about the uncertainty relation, I think you can just come and consult me. It's a very interesting topic, and we can have a lot of discussions about this, but I don't want to spend too much time on this point. Let me rather say what is the traditional uncertainty relation. This is a theorem. I will not prove it, but it's a theorem. And it says the following thing. It says that the variance, okay, let me first, sorry, messed up. Let me first define the variance of an operator. So the variance delta A on psi, well, is as usual the same thing as the variance. So the square of this would be the average of A squared on the state psi minus the average of A on the state psi squared. Okay, that's the usual definition of variance. And now the usual uncertainty relation, the Heisenberg I think it's called Robertson uncertainty relation, says that the product of the variances on the same state psi of A and B is upper bounded by 1/2 the expectation of the commutator on psi. Now, this is very popular. In my opinion, it's a bit overrated. Okay? Let me tell you why. At this stage, we have all the statistics. We have all the probability of A1 given psi, and we have all the probability of AK given psi for all k, and all the probability of BK given psi for all k. This is maximal information about our statistics. We cannot have better than that. In particular, if one of them or none of them is not 1, 0, 0, 0, 0, well, then there is some uncertainty. This object is a function of these probabilities. When you compute a function, necessarily you lose some information, or at best you keep it. Right? You cannot increase the information value. As a matter of fact, when you compute this function, you lose a lot of information. So there's nothing fundamental in the uncertainty relation. Those who call it uncertainty principle, well, it's not this. If you want, the uncertainty principle is this. That's a principle of uncertainty, that there will be intrinsic randomness in some cases, right? This is not an uncertainty principle. It can be, I repeat, it's a theorem. It could be computed. I don't want to do it now, but it's really a theorem. You can compute that these variances are lower bounded by these. And it can be useful in some cases, but it depends. Okay, this is all that I wanted to say about measurements. Again, I could say much more on the uncertainty relations, but I think maybe one day I will devote a full video to it, but in this moment, for the scope of this lecture, is not particularly important. I want to mention, just before moving to the next topic, which is the evolution of physical systems, postulate 3, I want to mention two things that I did not discuss in this introduction to quantum theory. One of them, let me write them down just for the sake of it. We'll write it here. Let's write it here. So, you know, at this point, as I told you last time, right, we have a syllabus to cover. There would be two topics that would fit perfectly well at this point. However, if I go into these, we will not have time to cover the whole syllabus. So therefore, well, I will leave it to other lecturers. So the first topic, so topics left out that would fit very well here. The first topic is symmetries. I mean, symmetries would mean the following thing, that, for instance, a change of basis, right? Something is invariant by rotation. Okay, I take scalar product, I do a rotation, scalar product remains the same, right? Or a Hamiltonian, we will see some examples later. But there is a whole theory of symmetries. Now, I just tell you the result. It's called Wigner's theorem. It says that symmetries are represented by unitary operators. And it's not surprising, right? Because a unitary operator is a change of basis. So a symmetry, you can always see a symmetry as saying, I change a basis and not much changes. Okay, that's the idea. There is something else. If it's a some discrete symmetries are anti-unitaries, but well, we don't need these in this course. So just keep in mind that anti-unitary means that is an operator that, for instance, well, that takes an anti-unitary operator is such that preserves the scalar product in modulus, but it would give it would give the complex conjugation here. But anyway, this is just a remark for you to know, but we will not use it. The second topic I will not mention, unfortunately, and I'm sorry for this, because it's a very interesting topic, is the description of composite systems. This gives rise to the notion of tensor product of vector spaces. And that's the context in which entanglement that you have seen a little bit in 6 quantum pieces appears. So, in other words, unfortunately, in this course, there is no more mention of entanglement, and you will see this in QM2. Okay, we can stop now.